Okay, and we're starting the recording here. So section 5.2, I'm going to let you copy this example down, a very important example, and then we'll discuss the solution. Okay, all right, so okay, so in this example, what we have here is we have a matrix A with some 2x2 matrix, and we have this dynamical system defined as x sub k plus 1 equals a times x sub k. And you've actually already seen this from section 4.9, for instance, if you have a migration matrix and you multiply the migration matrix, say by x sub 0, which would be the population distribution initially between, say, city and suburbs, well, that's going to give you the population distribution after 1 year. Similarly, if you want to find the population distribution of city and suburbs after 2 years, you can just multiply the migration matrix times x sub 1. So these are examples of dynamical systems. That's an example of a dynamical system. And of course, where k can be 0, 1, 2, 3, and so forth. In this case, k was 0. In this case here, k was 1. Okay, and what we want to do, and actually what we have here, well, this is actually interesting, right? Because, hold on just 1 minute here. Hold on. I got this example from the textbook in section 5.2 towards the end of the section. Okay, let me just double check it here. Yeah, it's actually example 5. But in fact, this matrix A is the migration matrix that we used from section 4.9. How many recall that? How many recall this is the same stochastic matrix that we used in section 4.9 for this? It was the migration matrix for the to model movement between the city and the suburbs. Okay, Eleanor recalls it. Thank you, Eleanor. Thank you, Hung. Okay, and Eleni, thank you, Eleni. So, okay, and initially, let's say that we start out with 60% of people living in the city and 40% of people living in the suburbs. Okay, well, we want to analyze the long-term behavior. Now we know from our discussion in section 4.9 where we found the steady state vector. I want to make sure I have that. The steady state vector for this matrix. We found that the steady state vector was equal to a vector with components 0.375 and 0.625, meaning that eventually 37.5% of people will live in the city and 62.5% of people will live in the suburbs. And again, we determine that by finding the steady state vector in section 4.9. Okay. Another way, of course, is to take you could take the matrix. Hold on. You could take the matrix A here, raise it to the kth power, multiply it by x sub 0, and look at the limit of this as k approaches infinity. That's an iterative way to also get the steady state for the system. And that iterative approach is mentioned in theorem 18 in section 4.9. But now we're in section 5.2, and we want to use 5.2 methods to analyze the long-term behavior of the dynamical system. In other words, we want to use section 5.2 concepts, eigenvalue, eigenvector concepts, to show that eventually 37.5% of people will live in the city over time, and 62.5% of people will live in the suburbs over time. That's what the population will stabilize to. So how would we do this? Okay, well, let's go here. First of all, we're going to find eigenvalues and eigenvectors. And you are used to finding those by hand. And certainly for your next exam, I'll be wanting you to find certainly some eigenvalues and eigenvectors by hand, working it out. You know, the eigenvectors, you have to solve a homogeneous system, do row operations, that sort of thing. But you can use, like for MATLAB, how would MATLAB find the eigenvalues and eigenvectors? Well, there's a command, and I spelled command wrong. It should be C-O-M-M-A-N-D. Okay, there's a command where it's called eig of sim of A. So what this is going to do is it's going to produce eigenvalues and eigenvectors in nice form, because as you have experienced in my math lab, it wants eigenvectors. Well, eigenvalues need to be in nice form, simplified radical form usually, and eigenvectors should be in simplified radical form, and that means usually fractions if possible. So if you type this command in MATLAB, let's see what we get. So I'm going to actually bring up my MATLAB here. Because I'd like it to be on the recording. This is the output we're going to get from MATLAB. Okay, this is what MATLAB should give us. These eigenvectors, these corresponding eigenvalues. let me show you in MATLAB that that's the case. One moment here. Okay, so we'll go back to this, don't worry. I know you're copying, we'll go back to it. Let me get the MATLAB here. Okay, can everybody see the MATLAB okay? Maybe give me a few thumbs up. Okay, good. Thank you, Abby. Thank you, Benjamin. So generally what I like to do is I like to open a new script, okay, where I can type my code here. So I'm going to type matrix. There's the matrix A. All right, now let me see. It's given me, you notice here, you notice in the top right, it's giving me a red box. Okay, that means there's a bad error. Usually means there's a bad error in the code. And so I can see right here, I shouldn't have a semicolon there. I should have a comma, right? And now, okay, I get yellow, which means there's a warning. But warning doesn't mean that the program won't run. It just means it says you can terminate your code with a semicolon. Well, I don't want to do that. I'm happy here. And then we're going to type in this here, VD in brackets equals I of sim of A. And what V is going to be, it's going to, well, I'm going to run the code here. So let me copy. Or I could do it one at a time, right? I could do it one at a time. I mean, let me just type in paste my code in here on the command line. Okay, yeah, that's the matrix we want. And then type this code here, hit enter. Okay, and okay, we got a V. Looks like a matrix. A V. It isn't a matrix, but let me just sort of tell you what's going on here. So what's happening is when you use this command ig of sim of A, the sim of parentheses A is designed to give you values that are nice looking, okay? And I will produce I want to be a little careful. Together with ig and sim, you get eigenvalues and eigenvectors. So the eigenvalues are located along the diagonal of the D matrix. Okay, the D matrix there. It isn't really, you understand, it's not like formally set it in the command line. It isn't like a formal matrix because you know a matrix would be like a 2 by 2. But what I'm saying is, look in D, look vertically. No, in D, look along the diagonal. You have eigenvalues of 23 over 25 and an eigenvalue of 1. Those are your eigenvalues. The eigenvectors come from the V. So looking at the V, if you look vertically, one eigenvector is -1, 1, and the other eigenvector is 3/5 1. So don't kind of worry. You might be wondering, well, gee, how can I make it like prettier? You know, you can work on that if you want. But, you know, we have our eigenvalues and we have our eigenvectors. We just got to interpret it the way I mentioned, and then you'll get eigenvalues and eigenvectors. All right, are there any questions so far? Okay, all right, well then let's go ahead and get back to the example here, the solution. Okay, so then with the command for an eigenvalue of 23/25, which is 0.92. 0.92 is what they have in the textbook. The eigenvector is -1, 1. And then for the eigenvalue equals 1, the eigenvector is 3/5 and 1. But what we're going to do is we're going to choose nicer eigenvalues, nicer eigenvectors. Well, the eigenvector of 1, -1, we're happy with that. That looks nice. But the eigenvector of 3/5 and 1, that second eigenvector, I'm going to do a multiple of that to get 3/5. What did I, for the eigenvector, for the second eigenvector, what multiple did I take of it to get 3 and 5 as my components? That's right, Eleni, 5. Very good. So when you take multiples of eigenvectors, those multiples of eigenvectors are themselves eigenvectors. Okay, multiples of eigenvectors are themselves eigenvectors. So this means then that, now let's see, the matter at hand is we want to analyze the long-term behavior of our dynamical system. Well, okay, so to do this then, we have to make use of the fact that the eigenvectors v1 and v2 form a basis for R squared. And so the initial vector, x sub 0, which was 0.6 and 0.4, that can be written, that's in two-dimensional space as well. That vector lives in two-dimensional space. So x sub 0 can be written as a linear combination of the two eigenvectors, because the two eigenvectors are a basis for R squared. They are a basis, right? You're used to the basis of for R squared of the standard basis, where the basis vectors are 1, 0, and 0, 1. But this could be a basis too. V1 and V2 could be a basis as well for R2. Now, what do you think we want to do for C1 and C2, given this vector equation? What can we do? What's the next natural thing to do here? X sub 0 equals C1 times V1 plus C2 times V2. What's the next natural thing that we want to do? What do we want to solve for? That's right, Hung. Solve for the C1 and C2. All right, so I'll go to the next page. May I go to the next page? Is everybody, want to make sure I'm moving at a good pace? And are there any questions? Okay. Well, all right. So I set up the augmented system here. All right. And you can solve that system and you'll find that C1 equals 0.225 and C2 equals 0.125. Okay, let me give you a moment to get caught up here. We're going to then go to here, but let me give you a moment to get caught up to here. Please let me know if you have any questions. Okay, so what we want to do here in this problem is, we're looking at x sub k, Actually, hold on, let me clear this. I mean, we're looking at x sub k, and we want to find the limit of x sub k as k approaches infinity. Now we know from section 4.9, we know that that is going to equal 0.375 and 0.625. Okay. We know that. Let's see if we can show that using the concepts in section 5.2. Well, first of all, let's look at x sub 1. X sub 1 is a times x sub 0. But x sub 0, because v1 and v2 form a basis for R2, those two linearly independent eigenvectors in R2 form a basis for R2. That means x sub 0, as you know, can be written as c1 times v1 plus c2 times v2. In fact, x sub 0 equals 0.225 times eigenvector v1 plus 0.125 times eigenvector v2. Well, all right, now I'm taking the matrix A and I'm multiplying that by this sum of two vectors. Well, matrix multiplication is distributive, so I get a times c1 v1 plus a times c2 v2. But then what I can do is the c1 and the c2, since they're scalars, by properties of matrix properties, I can pull those scalars out front of those products. But remember, what is a times v1? Well, v1 is an eigenvector, so a times v1 equals lambda 1 times v1. And similarly, a times v2, since v2 is an eigenvector, a times v2 is equal to lambda 2 times v2. And so the vector x sub 1 can be expressed then, well, we know what lambda 1 and lambda 2 are. No, I'm sorry. We know what lambda 1 and lambda 2 are. Lambda 1 is 0.92 and lambda 2 is equal to 1. So x sub 1 then can be that's the populate in this case, since A is that migration matrix from section 4.9, x sub 1, the population distribution after 1 year for people living in the city and the suburbs, that can be written as this linear combination of the eigenvectors of the matrix A, of the migration matrix A. Absolutely fascinating. Are there any questions up to this point here? Please let me know if you have any questions. All right, well, let's continue. Well, all right, so x1, great. What about x2? What about the state vector after 2 steps? You know, that x2 is the population distribution after 2 years for the city and the suburbs. Well, x2 is a times x1, but x1, okay, we know what x1 is. Let me see here, let me just, okay, this is x sub 1 here. So what I'll do is I'll substitute it in here, and then that's going to give me this. Now the lambda 1 is 0.92. I didn't bring 0.92 in here. I just called it lambda 1, but it's 0.92. Okay, so then again, we do the same kind of matrix operations we did above for x sub 1. And it turns out that x sub 2 is going to be equal to c1 times lambda 1 squared times eigenvector v1 plus c2 times lambda 2 squared times eigenvector v2. In other words, this is x2. What do you think x3 would be? We've done x1. We found an expression for vector x1. We found an expression for vector x2. And x1 and x2 are linear combinations of the eigenvectors. So we would think x3 would also be some linear combination of the eigenvectors v1 and v2. And I have 4 blanks to fill in. Okay, Hung, let me see. That looks right. C1 here, C2 here, and then we're going to have 0.92. Man, hold on. I don't like running out of room. Hold on. Hold on, class. C1 times 0.92 cubed times the eigenvector v1, okay, plus c2 times 1 cubed hold on, we're going to make it look good. All right, does there appear to be a pattern here? Yeah, that's right, Nafani, there is. There is. Are there any questions so far? Please stop me if you're uncomfortable. Okay. Well, then we'll go to the next page. In general, then, x sub k, which would be the population distribution in this case, for our example, of the city and the suburbs after K years, that can be expressed by this formula. We have a formula class. We found a formula. How many love formulas? Coming up with a formula. Yeah, Hung likes it. Eleanor likes it. Catherine likes it. Sure. Nema likes it. Yeah, I mean, okay, well, all right. Well, then we can, now what we can do, so, now at this point, see, I didn't put in C1 and C2, but now I'm going to put them in. Okay, because now I have my formula and I know what C1 and C2 are. C1 is 0.225 and C2 is 0.125. And so this is now my concrete formula. And as K goes to infinity, then, well, as K goes to infinity, what's going to happen to 0.92 to the kth power? What would that go to? What's that go to as K goes to 0? What's 0.92? 0.92 to the kth power as K goes to infinity. I mean, take like 0.92 on your calculator and raise it to the 1000th power and tell me what you get. Oh, Nafani has an answer. He gets 0, and that's right. So this means then that as K gets large, the entire first portion of the formula drops out, leaving you with 0.125 times 3/5, which in turn will equal 0.375 and 62.5. That vector will be the vector with components 0.375 and 0.62.5. And so here we showed a different way to find the steady state vector. So eventually, after a long period of years, the population distribution between the city and the suburbs will be 37.5% and 62.5%. City population stabilizes to 37.5%, and the suburb population stabilizes to 62.5%. So this is a really, I mean, how many think this is absolutely like beautiful? Yeah, Nafani's liking it. Benjamin likes it. Olivia likes it. Eleanor, yeah. I mean, Haley, oh man, yeah. I mean, this is, I mean, you're so used to, we love our calculus. We love integrating and taking derivatives. But, there's other fields of math. And this is one of them. And it's used a lot. All right, are there any questions at all? I think that's what I wanted to talk about here on this for section 4.9. Or sorry, 5.2. All right, I'll stop the recording.